Okay, so let's get going. Okay, so as we I love reading those comments. That's funny. Okay, so anyway, as we get going, as you recall from last time, we had switched gears by starting chapter 5. I had sort of teased what the subject is. We've been talking for the last 7, 8.5 weeks about rates of change. We first developed the idea of the limit. We then used the idea of the limit to develop a way of finding the tangent line, and then discovered that there's all this stuff you could do around that. There were rules for finding the tangent line is of course the derivative. There were special rules for finding the derivative depending on what type of function you had, whether it's a power function, quotient function, product function, composite function, etc. And there are these applications of the derivative. You can find rates of change in physical problems. You can you can use L'Hopital's rule. You can solve optimization problems. You can find extreme values of a function on an interval. You can even sketch the graph of a function just based on what you know about its derivatives. Although, to be honest with you, judging by the results of this week's quiz, I use the term we rather loosely. I can do it. Hopefully some of you will learn how to do it a little bit better. I will tell you, yeah, sorry, Maria. There's a comment about that. That quiz was a little bit rough, and I knew it was hard, but it's it's a difficult topic, and I was glad to see the results. I'm going to use it as a springboard for review. So that's. Oh, I'm sorry. I did not mean to call you out. I apologize. So okay. I was only sorry. Anyway, I was as I talk, I'm actually just referring to the comments as I read them, uh, as I read them on the screen. Anyway, so we're done with that, and we're now completely shifting gears. But then we're going to see what the relationship is to the derivative that we've done. What we're going to talk about now is area under the curve. So the problem that we want to problem that we want to solve is I want to be able to find this area. And the way that we're going to do this is we're going to use an approximation based on rectangles. I had drawn this the other night, that what I do is I subdivide the interval better. What I do is I subdivide the interval that defines the right and left boundaries of this region. And oh, sorry, let me just turn off the camera because we don't need that there. I want to subdivide the interval that defines the right and left boundaries of the region. And what I'll do is I'm going to draw a rectangle over each of these subintervals. So these actually get a name. I'm going to give them a name right now, even though we'll do this a little bit more formally later. What we call this first point x0. And if let's say that I've divided it into 4 subintervals, so this is going to be x4, and then I just give these points names like that. So you see it takes, in order to define 4 subintervals, it actually takes 5 points. And I can call the subintervals x0, x1. That's the first subinterval. That's subinterval 1, x1, x2. That's subinterval 2, and so on. So those are the kind of the names of the subintervals. What I'm doing is I'm using one of the points associated with each subinterval to define the height of each rectangle. So in this case, I'm using the last point in each subinterval to define that. And then what I can do is, that was the wrong way to do that. There we go. So that's rectangle 1. That's rectangle 2. That's rectangle 3. And not a good color for that. There we go. That's rectangle 4. So we're just going to add up all these rectangles, and that's going to give a pretty good approximation of the area under the curve. So what I've done here is, although there are a couple of different ways that I can subdivide the interval, notice that what I've done is I've drawn all subintervals to be equal length. So I've drawn them so they're all, I mean, sorry, when I say length, I mean the length from one end of the subinterval to the other. So it's, I don't have to do it that way. I could make them different lengths, but just for convenience, I'm making them the same length. The other thing I've done is to describe the height of each rectangle. I've to form the height of each rectangle, I've chosen the right endpoint of each of the subintervals. So here's the right endpoint of the first subinterval. And here's the right endpoint, x2 is the right endpoint of the second subinterval, and so on. So this rectangle here has the height f of x1. And this rectangle here has the height f of x2. This one has height f of x3, because I'm going to use the right endpoint of that subinterval. And this one has the height f of x, height equals f of x4. So what I'm drawing here has this name. It has the name the nth right endpoint approximation. What is n? N is equal to the number of rectangles. So what I've drawn here is the fourth right endpoint approximation of the area under f of x on the interval AB. I'm just waiting for some questions. Anyway, I generally don't like to make it a free for all, but let me just see. Oh, sorry. The question is, the notes for this chapter posted yet? I'm sorry. No, I didn't get a chance to do that before class. And unlock the audio. If you rejoin, there should be no way. You should be able to turn on your mic, your speaker, just not your microphone. I'm not sure what to do about that. Okay. All right. So let me continue. So this is not, of course, the only way to. This is not the only way to do this approximation. There's, as long as I'm drawing rectangles that are reasonably associated with the curve, I'm going to get some sort of approximation. So we could also do what's called the nth left endpoint approximation, or the nth midpoint approximation. Just briefly draw what those look like. So if I have this, it's A to B. If I want the left endpoint approximation, and sort of imagine what that looks like, what I would do is, if this is x0, x1, x2, x3, and x4, what I would do is I'd pick the left endpoints like that, so that the height of each rectangle is determined now by its left endpoint. And quickly shade those in this way. Okay, so that's the left endpoint approximation where I'm using here, I'm going to use f of x0, going to be f of x1, f of x2, and f of x3. So notice that in the right endpoint approximation, I never made use of x0. In the left endpoint approximation, I never make use of x4. And then finally, the midpoint approximation, draw like this, where what I have to do is in between, inside each of the subintervals, I'm going to draw another point that I call C1, C2, C3, and C4, and I use the midpoint of each subinterval to draw the rectangle. So now I get rectangles that look like this, that, that, and like that. So there we go. Okay, so in each case, what I'm doing now is I'm just picking some arbitrary point in the interval to serve as the basis for the height of the rectangle. A little awkwardness in the language, because I'm not actually using C1 as the height of the rectangle. I'm using f of C1 as the height of the rectangle, and f of C2, etc. So, and of course, there's nothing magical about having to use the left, right, or middle of the rectangle. I could, arbitrarily decide to use a point like that. As long as it's somewhere in the subinterval, I can use that point, plug it in to f, and get an appropriate height for the rectangle. So anyway, that's any of those would give a reasonable approximation of the area under the curve on the interval AB. So is there any question about that? You're actually, okay, so the question is, are we always going to use the right side points in this course, or will we use left and midpoints? The answer is you're always going to use either right, left, or midpoint. It is true that you could use any point, but I think that we have, just this semester, this is one of the new things, is we omitted the idea of using points in the middle, except for one very specific application, which you won't have to do anything. It's just going to be something I'm going to demonstrate a little bit later. I'm getting a lot of questions, and I'm just waiting to read them. So. Okay, let me just start answering. So the first question was, what's the point in using the approximation versus finding the area under the curve? The answer is that the formula for area under the curve comes from the approximation formula. So we don't just give a formula, because of course the point is almost never the point is almost never just to find the answer, but to demonstrate how you find the answer. So there will be questions where we ask you to actually find the approximate value of the area, using a particular type of approximation. I realize that some of you have already seen the formula for area under the curve, just as some of you saw the formulas for derivatives. And rather than just give you a formula, what I'm trying to do is develop where this comes from. And the first couple of sections of chapter 5, before they actually show you what the formula is for area under the curve, they develop it in this way because this is where it comes from. Next question is, won't the three methods give different values? And the answer is yes, they will. In fact, I'm about to demonstrate that fairly shortly. So let us actually do one of these problems. I just want to make sure I answered all the questions. Is there any time approximation is preferred? This is the only way on paper. Okay. So, okay, I think I've answered it, unless someone else had a different question. Okay, so this is a specific example of this. So let's actually draw this. Let's calculate. Oh, sorry, I just wanted to give you the actual terms for this. So we use the terms, the abbreviations rather. We say Rn is the nth right endpoint approximation of f on the interval AB. And Ln is the nth left that's the left approximation, and of course we use the term Mn for the nth midpoint approximation of f on AB. So the reason, by the way, that I rewrote the f on AB is that I just wanted to emphasize that it's not possible to say what's the nth right endpoint approximation. It's not even possible to say what's the nth right endpoint approximation of f. You have to talk about, for any of these, what I need is I need a function and I need an interval. Without those two things, the function and the interval, talking about the area is meaningless. So even though this symbol Rn does not include the f or the AB, that's implied. In other words, I have to say what is Rn for for a particular combination of f and AB. In this case, just going back a minute, what this is showing, this is a picture of R4 for f of x on the interval AB. That's what that's a picture of. So that's how you use that notation. So let's go to this problem where we're going to calculate R6, L6, and M6 for f of x equals 1 over x on the interval 2, 4. So let's just draw briefly what we're describing. The function 1 over x looks like that. Y equals 1 over x. And we have here the interval. Let me just draw it a little bit bigger. Not going to draw it to scale. So we have the interval 2, 4. So what we want to find really is this. We're trying to find is this area. And we're going to do it by drawing these rectangles. Rectangles at these subintervals where the green lines are. that gives us 6 subintervals, and we're going to use that to find the approximate area. So first do R6. All right. First thing you need to do is observe that right in the middle there is 3. And here I have, it's going to be 7/3, 8/3, 9, 10/3, 11/3. So those are the values of those are the values of the points that define these subintervals. And give them names. If I want to name them, that's x0, that's going to be x6, and that's x1, x2, x3, x4, and x5. So notice that for any approximation with six subintervals, the last endpoint is going to be called x6. The first one is going to be called 0, and we're going to have a total of 7 of them. Notice, by the way, that x0 is always the same point as A, and xn, the last one, is always the same point as B. Okay. The other thing to take note of is that each of these rectangles has the same width. The width of this is, in this case, you can see that it's 1/3. So where do we get that from? What we do is we take B minus A and divide it by the total number of subintervals, and that gives us the width of the subinterval. So in this case, that's going to equal 4 minus 2 over 6 subintervals is 2 over 6 equals 1/3. Okay. So, all right. So what we need to do now is sorry, I just lost my notes on this for a minute. Where did they go? Oh, there they are. Okay, got it. Okay. So in order to calculate R6, keep in mind that what we're focusing on are these are going to be the 6 points that give us the height of the rectangle, the right endpoints of the interval. So for R6, we're going to have 1/3 times 1 over 7/3. In other words, that's the first rectangle. Back up for a minute. That's the first rectangle. The height here is f of 7/3, and the width is still going to be 1/3. So that's the width, and that's the height. And then we keep adding. So we're going to do 1/3 is still the width of the second rectangle. That doesn't change. And that's going to be 1/3 times 1 over 8/3 plus 1/3 times going to be 1 over 3. I'm using 1 over these numbers because of what the function is. In other words, this is f of 7/3. This is f of 8/3, etc. So I keep going. 1/3 times 1 over 10/3 plus 1/3 times 1 over 11/3 plus 1/3 times 1 over 4. There we go. So simplify this a bit, this is going to be 1/3 times 3/7 plus 1/3 times 3/8 plus 1/3 times 1/3 plus 1/3 times 3/10, 1/3 times 3/11, and 1/3 times 1/4. That comes out to 1/7 plus 1/8 plus 1/9 plus 1/10 plus 1/11 plus 1/12. Isn't that convenient? And when we do that, if you add it up, the example actually came from the textbook, you get 0.653 approximately. So that's the approximate right endpoint approximation. Why didn't you do 1/3 times 1/2 for the first number? Oh, okay. Good question, Logan. That's because this is the right endpoint approximation. So I'm considering not the first point, but rather the first subinterval there. So by using the right endpoint approximation, I'm using the right endpoint of each subinterval. So the 2 never comes into play. Okay. So if I calculate instead L6, so now what I'm going to do is instead, I was trying to figure out how best to depict this. I'm going to use that point, that point, that point, that point, that point, and that one. And it's the last point that gets omitted. I don't want to belabor the point, but basically what this is now going to be is 1/3. That's the width again, still the width. And it's going to be, now I'm going to use 1/2. And then I get 1/3 times 1/7/3 plus 1/3 times 1/8/3 plus 1/3 times 1/3 plus 1/3 times 1/10 plus 1/3 times 1/11. And this gives us, we add all that up and simplify, that comes out to 0.737 approximately. Okay. Anyone have any questions about where those numbers came from or what they mean? All right, good. No questions. So let's feel free to ask. Get one. So for the midpoint, we need something a little bit different because now, just draw this again. I've got 2, 4, putting in those numbers. What I actually need is I need to be able to draw, I need to be able to choose a point that's in between them. These are really the points that I want to use as the height to form the heights of the rectangles. So I actually need to calculate more values. This is going to be 6/3 plus 7/3 is 13. That's going to be 13/6. And this is going to be 15/6, 17/6, 19/6, 21/6. I guess could also be, could divide that by 3 and get 7/2. Or, and then this one is going to be 23/6. I was just waiting for a question before I go on. Okay. All right, so for this, I still have the same width of each rectangle. In other words, each width is still going to be 1/3. It's still going to be 1/6 of the entire interval running from 2 to 4. It's just that I'm choosing a point in the middle of each interval. So this is going to be 1/3 times 1/13/6 plus 1/3 times 1/15/6 plus 1/3 times 1/17/6 plus 1/3 times 1/19/6 and 1/3 15, 17, 19, 21. Yeah, okay. 1/3 over 21/6 and 1/3 over 23/6. And that comes out to 0.692. I guess I should probably emphasize this is just an approximation of that. So okay, so as somebody pointed out earlier, we do in fact have 3 different values depending on which approximation we use. An interesting question is, so can't we just do R6 over 2 plus L6 over 2 to equal M6? Does that come out the same? Trying to think if that always comes out the same. Actually, no, it doesn't. That's an interesting point. Give me a second. It doesn't come out the same because let me just give you an example of where it wouldn't come out the same. I want to see what the other questions are. It's actually an excellent question. Probably more accurate. The interesting thing actually is no, it's not. It depends on certain things about the function. That's a really interesting question. We usually save that topic for Calc 2, but it's sort of impossible to talk about this topic without at least giving you a little bit of a sense of it. So I'll turn the page. I'm going to come back to this for anybody who wants to see this page again. But I just want to draw an example of this. Let's suppose that I'm going to use 4 subintervals for a function that looks like this. Okay. So it's sort of great how when you teach these classes, you can come up with the most pathological examples like this. If I use the right endpoints, I'm going to choose these points here, right? And if I choose the left endpoints, highlighter for that. So the yellow highlighter shows what would happen if I pick the left endpoints, and the red dots show what happens if I pick the right endpoints. Notice that the rectangles are going to be the same height, whichever one I pick. But if instead I decide that I want to pick the midpoint, then I'm going to pick these points. So that's going to give me systematically higher values if I pick the midpoint than if I pick either the left or right endpoint, thereby showing that the midpoint approximation in this instance is not going to be just the average of the left and right endpoint approximations. Truth is, you can't really say which of these is the most accurate without you can't really say which of these is the most accurate without some understanding of what the function is. But there's always a way to draw this, really quite pathologically, so that neither of them is going to be so that you can say that one of them is more accurate than the other, and it's not always going to be the midpoint. You might think actually that the midpoint gives. Many people think the midpoint just gives the exact answer, but this diagram also shows why that's not true. It really depends very much on the function. Sorry, there's a question. Someone says it comes out to 0.695. I'm sorry, I just wanted to clarify what you're saying comes out to 0.695. Are you saying that's the exact answer? Oh, for the average. Oh, okay, I see. Yeah, so you see the average is actually a little bit different. You can actually kind of see why, because this function has a decrease. It starts out steep. It starts out having a very negative slope, and its slope is actually increasing. Um, so what that means is that actually the decrease from the beginning of each subinterval to the end gets more shallow. So actually it takes a lot of its decrease to the right left end of the subinterval as opposed to the right. And that's why the midpoint doesn't give you the exact average of the two endpoints, even in this function that looks very regular, unlike the one I just drew. So um, and this is, one of the points that we're covering is that there's really no easy way to get these areas. The only way to do it is to use the only way to get the exact area is to use calculus. You can get a very good answer using rectangles, but not not necessarily an exact answer. So okay, so we use summation notation as a way of writing. Okay. Sorry, I was just reading my notes. Okay, so does anyone have any questions about how to do a right, left, and midpoint approximation? Okay. So two questions are: how do you choose the subintervals, and what is a go-to formula for the right endpoint approximation? Actually, those are sort of going to be answered together once we get through a little bit of notation. The go-to formula for right endpoint approximation, I just need to introduce a new symbol in order to do that. As to how you choose the subintervals, that's not that hard if you know what the original interval was, and if you know what the original interval is and how many subintervals you want, it's fairly easy to choose the subintervals. In other words, assuming that I'm going to, and don't even worry about what the function is, but I'm going to integrate over a through b. And if I say that n equals, happen there. How do you choose how many subintervals? That will be given in the problem. So in the previous problem, it was called R6, M6, and L6. So what that's saying is there would be six subintervals. Yeah, it wouldn't make sense to ask for an the question is that always going to be given? It wouldn't make sense to ask for an approximation without specifying the number of subintervals. Okay. All right. So this is where we start to get to a point where I can introduce the formula for the approximation. So we're going to introduce this notion of this notation called summation notation. I think some of you have already seen this in pre-calc, but I just want to make sure everyone understands what it means. If we have a series of numbers, a sequence of numbers that we want to add up, rather than having to write out all the numbers, there's this sort of compact way of writing it. This symbol is the Greek letter sigma, capital sigma. And we use the S for sum. So the notation is this, is that if I have these numbers, which I'm going to denote by a subscript, I'm going to say that they're am plus 1, all the way up to some number an. So just for example, maybe I have a3, a4, dot, 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 all the way up to a15. So in this case, m is equal to 3 and n is equal to 15. 3 is the lowest index, 15 is the highest index. If I want to add them up, I could just write out, I could just do what you see here on the left, where I just have, I got to get my pointer out, where I just have plus signs, separating all the numbers. But a sort of cleaner way to do it is to write the sigma symbol and write k equals m through n of ak. And what that means is that you're going to cycle through all the integers starting at m and going up to n, and you're going to add them together. There's actually a related symbol, capital pi, from k equals m to n, which of ak, which is equal to am plus 1, an, where it's pi for product, and you're actually multiplying all the numbers together. We don't really do a lot with that, but this is sort of common in math, is that if you want to, you just cycle through all the integers from something up to something, you use a notation like this. So I'm going to erase the product one because we don't use it here. We're going to use the sum one. So here's just an example. If I have, if let's say, I have these three numbers, a1 is 6, a2 is 14, and a3 is -5, then I could write something like this. The sum from k equals 1, and the way I'm pronouncing it, by the way, is exactly how you would say this symbol. The sum from k equals 1 to 3 of ak, and that is equal to a1 plus a2 plus a3. Since I know what those values are, I would just be adding them up, and I get 15. It's important to recognize that these sums, once you know what the numbers are, the sum itself comes out to a number. It doesn't, we'll get to a situation later where it has a variable in it, but usually you're not going to see a variable in the final answer. So here's sort of a good example is what is the sum from k equals 2 to 6 of k itself. So here, what that's going to be is I'm going to go from 2 to 6, where in every instance, this is going to be k equals 2, k equals 3, k equals 4, k equals 5, and k equals 6. And then for every one of these terms, I'm just going to replace whatever comes after the sigma, which in this case is just k itself, with the value of k. So this is going to be 2 plus 3 plus 4 plus 5 plus 6. And that comes out to 5 and 4 is 9, and 5 is 14, and 6 is 20. So that expression, this expression here, has a specific numeric value, which is 20. Okay. Any questions about this? With decimals, you mean like where the index is a decimal, right? No. The one feature of this notation is that you're always dealing with integers. There is I should say that if you go way beyond this in calculus, if you go up to like the course that's called either advanced calculus or real analysis, you can sort of generalize this sigma term to do sums over something other than the integers. But for calculus 1, 2, and 3, we're gonna stick with the integers entirely for indices. Okay. So a couple of properties. Um, this is what's called linearity of summations. Um, and this is very similar to the linearity rules that we already saw for limits and derivatives. So first of all, if I have the sum of two different expressions, I can just break them up. And you can think of this as the same sort of thing that we had, just like the limit of a sum is equal to the sum of a limit. The limit of the derivative of a sum is equal to the sum of derivatives. Just the same, I can do that with summations. So I just want to make sure I have an example of that a bit later. The example fell off the page I had. I'll have to make one up. Okay, so first of all, you can add, if I can add summations. It's also the case that if I have the sum of some constant times these terms, times the terms, I can just pull the constant outside. And finally, it's the case, this is possibly the last one, is the easiest one to see, is the sum from k equals 1 to n is just equal to n times c. This should be fairly clear. I'll just write the last case here. So here I've got k equals 1, k equals 2, k equals 3, k equals n. So I'm just putting in a value of k for each value of k that could possibly exist between 1 and n. And then what I have to do is just substitute wherever I see a k in the expression after the sigma, I substitute the current value of k for that for that term. The thing is, there is no k in this expression. There is no k after the sigma, so I would just replace the k with 1, but there is no k to replace. I just get a c. I replace the k with 2, but there's no k to replace. I get c, and I just keep doing that. So what I'm doing is I'm just multiplying c. I'm just adding c to itself n times, and you can see that that's equal to nc. Okay. This one, let me just come up with two examples here. Let's suppose that I have the sum from k equals 1 to 5 of, make it a little easier, k3 of k squared plus k. So that is going to equal the sum from k equals 1 to 3. I'm applying rule 1, by the way, here. K squared plus the sum from k equals 1 to 3 k. That's what rule 1 means, is that I can break up that sort of sum in that way. So this is just going to equal 1 plus 1 squared plus 2 squared plus 3 squared. This is equal to the sum from k equals 1 to 3 of k squared, and then plus 1 plus 2 plus 3. Going to be the sum from k equals 1 to 3 of k. So this is just going to be 1 plus 4 plus 9 plus 1 plus 2 plus 3. That equals 5 and 9 is 13, and 6 is 19. But notice that all this really means is that I could have written this, if I were going to do it directly, I would have gotten 1 squared plus 1, 2 squared plus 2, and 3 squared plus 3. So all that this rule really means is it's the commutative property of addition. It just means that I can rearrange things on different sides of the equal of the plus sign, and I get the same sum. So I wanted to see if there was a question about that. Yeah, go ahead, even if it's unrelated. What happens if k is even while n is odd? How would you count the last case? I'm not sure what you mean. First of all, k isn't either even or odd. K is like a counting variable. It cycles through all the numbers between the lowest and highest numbers. If what you're imagining is that maybe there's some case where there are only there are 4 instances of k squared, but there are only 3 instances of k, that's not going to happen, because the assumption that's built into this is that I'm counting from 1 to 3. I'm going 1, 2, 3. So there are going to be exactly 3 instances of each case. You always start from 1? No. Here, you start from m. It's very common that we're going to be dealing with series that start from 1. And by the way, the name for this, the name for adding up a whole bunch of terms is called a series. That's the word for it. So usually you're going to start with 1. Sometimes we'll start with 0. You can theoretically start from any integer. You could go from negative a million up to negative 900,000. It's, as long as the bottom one is numerically lower than the highest one, you can count from one to the other. And do an example where k equals m, sure. Let's see. Do that actually. Let's do some. I'll just demonstrate. This is demonstration of rule 2. So we just number that as rule 2, and that's 3. We already had a demonstration of 3, so I'll demonstrate rule 2 while also showing one where k equals something other than 1. So let's do k equals 5 to 7 of 2k squared. So that's going to be here. I'm going to do k equals 6, k equals 7. So those are the only 3 values of k that are going to appear in the summation. This is going to be 2 times, I replace the k with a 5 squared like that, plus 2 times 6 squared plus 2 times 7 squared. So that equals 2 times 25 plus 2 times 36 plus 2 times 49. And that should come out to 5, 36, 49, 110. So this should equal 220. And by the way, the rule that's being demonstrated here is that I could have just said that this is equal to, because this is like a constant, I could have pulled it out and just said that's equal to 2 times k equals 5 to 7. k squared, which is going to be 2 times k equals 5, k equals 6, k equals 7. That's going to be 5 squared, 6 squared, 7 squared. So that's 2 times 25 plus 36 plus 49. And that gives you the same value, 220. So again, what this is really saying, this is really the distributive property. So yeah, 5 equals m in that case, yes. Okay. Okay. Just a second. All right. So let me show what this has to do with the topic that we're doing. Let's go back this picture. Okay, so we're back to the right endpoint approximation picture. All right. So recall that I said that we're going to number these x0, x1, x2, x3, and x4. So if you think about what this is, if I want to describe R4 with, again, this is the function y equals f of x, there's a little bit of terminology I just want to introduce. This distance, the width of each subinterval, this is equal to b minus a over n. In other words, the length of the subinterval, which is b minus a, divided by the number of subintervals. And that gets the name delta x. We've seen delta x before, and this is another use of that. In other words, that's the change in x. As you start at a and you want to go to the next subinterval, you go delta x to the right. So what that means really is that this first rectangle, I'm just going to number the rectangles. I'm going to number the 4 rectangles. The first one is going to be, put in the points that I'm using here. This is going to have a height of f of x1, that's the height of the rectangle, times its width, which is delta x. I know I did the delta x here over the second rectangle, but the point is they're all the same width. So there's that. The second rectangle is going to have a height of f of x2 times delta x, which is, and third rectangle, f of x3 delta x, and the fourth rectangle is f of x4 delta x. So I can write this in this form. If you look at what I'm adding up, this is going to be the sum from k equals 1 to 4 of f of xk delta x. So this is the summation form of a of a right endpoint approximation. And not surprisingly, the left endpoint approximation, where I'm going to be choosing instead, I'm going to be choosing this point, this point, this point, and this point. L4 is going to equal, that's going to be f of x0 delta x plus f of x1 delta x plus dot 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 f of, I'm only going to go up to x3 delta x. So that's going to equal the sum from k equals 0 to 3 of f of xk delta x. So this is the way that we would write or that we would write an approximation using summation notation. And the answer is, the reason this is useful is that I can write Rn being the sum from k equals 1 to n of f of xk delta x, and ln equal to the sum from k equals 1, from k equals 0 to n minus 1 of f of xk delta x, where in all cases delta x is just another name for b minus a over n. Yes, so these are the formulas that you can use to find the right and left endpoint approximations. Okay. So write that a little neater when I clean these up. Okay. Let me just see. Oh, is there a question? Is delta x a constant? So just a second. I want to answer that. There's a chat between two students. I certainly do like to see people discussing things. I just don't want to end up leaving people a misimpression. It is correct that delta x does not, in the most general case, have to be a constant, but we are going to deal only with situations where delta x is a constant, where we divide the original interval into subintervals by making them equal with subintervals. They don't have to be, and as we get to the exact definition of area, it's provable that it doesn't matter whether they're the same width or not, but just for simplicity, we're going to treat them all as the same width. What I did say we would cover in this class, however, is the situation where the point we choose to represent the height is neither the right endpoint, the left endpoint, nor the midpoint. That we will use when we get to the theorem that gives the exact area of under the curve. Okay, so let's see. We have a couple of formulas that are kind of useful, which is it's often useful to be able to add up certain very regular series. So if I want to add up the first n positive integers, the formula to do so is, which is what sum from any k equals 1 to n of k means, the formula to do that is n plus 1 over 2. And if I want to add the first n positive squares, the formula to do that is n plus 1, 2n plus 1 over 6. So just for, and there's also a formula for k cubed. We don't use it very much, but you can see it right here. It's in the textbook. I do feel that everybody should know these two formulas because they are actually useful in solving problems. I have not yet seen some. I've not yet seen somebody be asked to use the the third one from memory. Is a question: is there a reason why they are uppercase n? The answer is yes. In general, I'm going to use, when I write a constant, when I'm using a letter to refer to a constant rather than a variable, I'm going to use capital letter. And as you recall, what we're trying to do is write something like Rn as a summation, and I'm using n to mean the specific number of subintervals. You know, it's a constant. I don't know what it is, but it's also not a variable. It's just representing some number that I haven't specified. So here what we're saying is I'm adding up not the first arbitrary number of numbers, but specifically I've chosen some number n. I'm going to add up the first n numbers. So just as an example, sum from k equals 1 to 5 of k, which equals 1 plus 2 plus 3 plus 4 plus 5, equal to 5 plus 1 over 2, which is 30 over 2, or 15. And if you add up 1, 2, 3, 4, 5, that is in fact what you get. Sum from k equals 1 to 3. It's a little harder to do this because the numbers are so big. Of k squared is going to be, that's equal to 1 plus 4 plus 9. That's equal to 3 times 3 plus 1 times 6 plus 1 over 6. So that's 3 times 4 times 7 over 6, which is 12 times 7. It's 84. All right, yeah. Yes, 84 over 6, which is 14. 84 over 6, which is 14. So that does in fact work. Okay. So now why would we want to know these formulas for power sums in calculus? Let me just get to the point that we're trying to make with all of this. What we want to do is define not an approximation of the area, but the exact area. The thing you have to recognize is that the reason that this, I'm going to take like a depiction of R3. This is what I'm drawing here is R3 for some function. The reason this is only an approximation of the area is that I'm very crudely assuming that everything that happens on this interval can be represented entirely by that point. And of course it can't. There's a lot going on in that interval that point just does not capture. So if I want to make it a better approximation, let's take the same function. I'll try to draw exactly the same function. What if instead here I've drawn 9 intervals. So this is going to be R9. And now that, etc. I don't really have to draw them in, but hopefully you get the point, is that by making the ends of the subintervals much closer together, I'm eliminating a lot of the problem that there's all this area that's not represented by the red point because I'm putting the points much closer together. So why don't I instead, oops, not that, Question is, why don't I instead just write, instead of writing here, I have R9, why don't I have R100, where I divide this into 100 subintervals like that. I can't really draw 100 subintervals, but if I could, you can imagine that you get a much better approximation of the area. Well, if you think about where we're always going with this in calculus, is where we're going is we're saying, what if instead I find R infinity? But I can't find R infinity because infinity is not a number. And at the very least, I can't actually say what's B minus A over infinity to find the width of the subinterval, or I could. That becomes 0. So now what I have is an infinite number of rectangles, each of which has 0 width. That doesn't really make any sense. But what I can do is I can define them as a limit. So I can say the limit of, if you look over here, I can say the limit of Rn as n approaches infinity. And I can actually do the same with the limit of mn, the midpoint approximation, and the limit of ln, the left endpoint approximation. And so this theorem says that if f is continuous on AB, then all three of these approach the same number, and we simply define that number, at least as long as f is a positive function, we define that number as the area under the curve. So how would we use that to define area? Let's just do a really simple example. Let's find the area under the graph of f of x on the interval 0, 4. First, let's just be clear on what I'm drawing here. What I'm drawing is that's y equals x, and I'm simply drawing this triangle. It's a right triangle. Its width is 4, its height is 4. The area is equal to 1/2 times 4 times 4, which is 4. No, sorry, 8. Is 8. Let's imagine that what I want to do instead is I want to divide it into rectangles like this and just let the rectangles get infinitely skinny. You can see how 4 rectangles is clearly going to overshoot the area. But if instead we imagine infinity rectangles, I could get the exact area. So let's set it up like that. Here what we have is we have each rectangle, that's A equal to 0. This is B is equal to 4 because I've got the interval 0, 4. So what that means is that delta x equals B minus A over n is equal to 4 minus 0 over n, which is 4 over n. It's also going to be the case that if I divide it into n rectangles, then call that x1, x2, x3, and x4, then xk is going to equal k times the width of the rectangle, because what I'm doing is I'm just sort of kicking the point one unit to the right. So k delta x, or k times 4 over n, like that. So what that means is that Rn is going to equal the sum from k equals 1 to n of f of xk, which is k times 4 over n, times delta x, which is 4 over n. But we know that since the function f of x just equals x, this itself is k over n. This just equals k times 4 over n. So this equals the sum from k equals 1 to n of k times 4 over n times 4 over n. So that equals the sum from k equals 1 to n of 16 over n squared times k. This is a constant. N is not a variable, it's just a constant, so I can actually pull it outside. And equal, so this is going to equal 16 over n squared times the sum from k equals 1 to n of k. The limit of Rn equals limit as n approaches infinity is equal to the limit as n approaches infinity of 16. Sorry, I know I'm a minute over time. I'm just going to try to finish this really quickly before we leave. 16 over n times the sum from k equals 1 to n of k. We already know how to find that, so that's going to be the limit as n approaches infinity of 16 over n squared times n plus 1 over 2, which equals the limit as n approaches infinity of 16 times n squared plus n over n squared times 2. And we see that we have n squared as the highest power in both cases. That means that this is going to equal 16 over 2 times the limit as n approaches infinity of n squared plus n over n squared. This limit is equal to 1. This expression is equal to 8, and we get the same number, 8. And that's expected because that's what we thought the area was going to be. Okay. Any questions about that? That's I know that's a lot of material to absorb. Oh, good. Okay. So, all right. Anyway, I'll let you go. Hope you have a good rest of the week. You are welcome. Do. Everyone have a nice rest of the week. I will.